Hello. Here's a separate video of what we're doing in class today on isothermal processes. So this, oops, aha, I wanted to split it up into two videos. Isothermal processes. So an isothermal process, remember we had isochoric, constant volume, isobaric, right? Constant pressure. And I erase that because I'm just going to write it like this. Isothermal is constant T, right? So again, we're assuming constant N. So from a ratio standpoint, we can see that this is constant and this is constant. Therefore, P should be inverse to V, which means P1V1 equals P2V2. Let's see if conceptually we can produce that same result. What does this mean physically? So this is the ratio that you would use in an isothermal process. But a few things here. How do we create an isothermal process? And how does this manifest mechanically? So remember, isochoric and isobaric are powered by heat conduction, positive or negative Q, which means that they are driven by, you have a container, it's either rigid or not, and you heat it up or you cool it down. And so it either expands or contracts based on the pressure. So the heat conduction causes a delta P, and the delta P expands or contracts the container or not, right? If it does expand or contract the container, that's isobaric. If it doesn't, that's isochoric. Because if it expands or contracts, the pressure then equalizes again. If it doesn't, then the pressure just builds and it just stays there like a pressure cooker, or it stays there like a low vacuum system that wants to implode, right? Cool, right? So that's review. So what's isothermal? I'll just tell you, it's powered by an external force or an external pressure. So if I have a piston, so this is the classic example. I'm hoping to find one to have in class. If I have a piston is a sealed container where this can move up and down, right? It's sealed, so nothing can escape. And now you're like, oh, right, I've seen this before, or maybe you thought of this before. If I push down on the piston, so here we go. Here's me trying to draw a piston in a container. It starts off at some initial volume, and it starts off at atmospheric pressure. And if I push down, so push down, then what happens? Well, the volume clearly gets smaller, right? So V2 is less than V1, and as a result, P2 is greater than P1. And as we're going to see, pushing down actually adds energy. And so what we need is actually heat to leave, because this is adding what we call work. I'll formally introduce that a little later. So I'll just let you know that's what's happening. But the whole point is that if this is not insulated, so the temperature can regulate with the outside, then T is constant. In fact, if I didn't even mention the work and the heat thing, you'd probably say, well, the temperature is constant because there's no reason for it to change. it's connected to the outside. The outside regulates its temperature, so T is constant. So what do I have? Well, if volume goes down, pressure goes up. Volume goes down because of the external force. Right? Which increases the pressure. You can think of it as like the outside force adding pressure because it's pushing on it, right? And then the opposite's true, right? So this is 1, this is 2. It's easy, right? 1, again, we'll start with atmospheric pressure. And then pull up. Well, if I pull up, what happened? V increased, V2 is greater than V1, and that because here, less space, more collisions. Here, pressure will decrease because less, that. I'm confusing the two. I forgot to write it for up here, right? So sorry. Let's go back. So for this first example, right? Example 1, example 2, step 1, step 2. So I push down, the volume decreases. Yeah, less space, more collisions. I did have it right. And here it's more space, so less collisions. They're inverse, right? Fewer collisions, because more space, fewer collisions. So pressure decreases. P1 V1 equals P2 V2. That's it. Pretty straightforward. So we have our pressure and volume being inversely proportional if it's not insulated, so T can regulate with the outside, therefore temperature is constant. We can do a quick little, like volume 1 is 1 liter, pressure 1 is 1 atm. If I reduce the volume to 250 milliliters, what is P2? Pause the video, see if you can figure this out on your own. Go ahead, pause it. Pause it. Do it on your own. Oh, right, 250 milliliters. So now unpause it. 250 milliliters is 1/4 of a liter. So volume went down by 1/4, therefore pressure goes up by 4. There's a cool way of looking at it. Therefore P2 is 4 atmospheres. So 4 times 101,325, whatever that is in actual pascals, 405,300. Did I do that right? 405,300. I think I did. Because 4 times 25 is 1. 4 times 13 is 12. So 405,300 pascals. I think I got it. Correct me if I'm wrong. That is the pressure then in the container. And that's why there needs to be an external force, is because when it's pressurized, obviously there's going to be, right, an external force down, there's going to be a pressure gradient up. So no longer is this like this is sort of a flexible container, but it's like you're purposely squeezing. Like if you purposely squeeze that plastic bottle in class, there's an example, right? If I purposefully squeeze it with my hand, right? I'm applying a force. What happens? The volume goes down, and so therefore the pressure goes up in the bottle. And if you've ever done this, you can like squeeze so hard you like pop the top off because there's a delta P pushing up. It's like you're applying force that goes into the molecules that then comes out the top. And the whole point is that the force you're applying is the delta P times the area. So it's a cool way of looking at it is that the external force you're applying, right, creates the pressure gradient, because that's ultimately what's happening here. If you wanted to do this with just the equation, you would do P1 V1 equals P2 V2. Again, you can use converted units or not, but you do need to convert one of these to liters or one of these to milliliters. Maybe you can convert this to milliliters and write 1 atm times volume 1. Again, I can keep this in atm or use 101 through 25 PA. Right, I can do one or the other. Right, because it's a ratio. I'm just gonna use one because it's easier. And I'm gonna use 1,000 milliliters as V1, and then P2 is what I'm solving for, equals 250. I'm gonna get that P2 is 4 ATM. I like it like this though. This is a fun way of doing it, but plugging it in will also get you there. It's all good. Here's my answer in pascals if I want to convert to pascals. Or if you did pascals right off. Ratios are the best. Ratios. It's so great. Just have to be Kelvin. You cannot use Celsius. There's the concept. There's the math. And we got it all. Isothermal